All right, so we finished up yesterday taking that P of X right there, okay, and we factor that. Now we factor it by grouping, all right? I think it's a good idea, guys, to start maybe developing a little bit of maybe a hierarchy of tools or factoring techniques to always kind of address. You know, I would always do GCF. Do GCF first, okay? Is there a greatest common factor going to bring out of everything? Because that's just going to make things a lot simpler, especially if my final kind of determination is to use the P over Q stuff. If there's a GCF that I can take out before I do P over Q, that's going to make my life so much easier, okay? So I'm going to do that. I'm going to then look to see if there's any quadratic techniques, meaning, you know, if it's a quadratic function, can I, you know, do AC method? Can I do product sum technique? Can I do, you know, quadratic formula, that kind of thing? Okay. Now, when I say quadratic techniques, I'm even saying maybe quadratic form. If it's x to the fourth, and then there's an x squared term and then a constant, maybe it's quadratic form, so I can address that way. If it's x to the sixth and then an x cubed and then a constant, it's quadratic form, so we can address it that way. So when I say quadratic techniques, I don't just mean things that are x squared. It could be of like I'll show you here. Ax to the 2n plus bx to the n plus c, where n is just an integer, right? N is equal to 1, 2, 3, 4, 5, and then that would give you the idea that, you know, if n is 2, that'd be x to the fourth plus x squared, right? Okay. That's quadratic form, and you can factor that way. So I would address the next thing I would do, guys. Try factor by grouping. Okay. If I can factor by grouping, that's going to save me a lot of effort and time on rational root theorem. Okay. If none of that stuff works, then I get rational root theorem, which is my P over Q stuff. I'm not saying that that's set in stone in regards to a hierarchy, but I mean it's something to kind of address and look at and use. Okay. I think that is the best thing to do in regards to saving time. All right. When you guys get to a calculus class and you got 6, 7, 8 questions for homework and it's bouncing back and forth between all these different types of factoring techniques, you don't want to just say, oh, I'm going to use P over Q every single time, because now you're wasting maybe 5 to 10 minutes with each one of those questions where maybe they're designed to attack or be attacked by a quicker approach. Okay. So that's what we did here. We went through there and we got the factor by grouping, and that made more sense to factor by grouping, right? I'll look at the first two. We can bring out an x squared. Look at the back two. I can bring out a 1. We got x squared plus 1. And then it left me x minus 3. Okay, so the x minus 3 is right there. Now the x squared plus 1, we were able to break that down further, right? Because we have the fact that the square root of negative 1 is equal to I. So we basically took x squared plus 1 equals 0. We solved that for x. And once we solved it for x, we can work our way backward to get the factors x minus 9x plus I. Okay? So that's how that thing's factored. And we talked then yesterday that is an example, that models exactly what we were mentioning in these two theorems. Okay? This theorem here is the fundamental theorem of algebra. It was saying that when you take a polynomial and you factor it, okay, as long as my n is greater than or equal to 1, okay, and it's an integer, okay, so n the first, second, third, fourth, whatever, okay. When we do that, we're going to get at least one complex 0. I mean, if it's the first power, we'll get one complex 0. If it's the second power, we'll get two complex 0s. Third power, 3 complex 0s. And that's what we got in ours. It was to the third power, so we got 3 complex 0s. Okay, x equaling 3, x equaling I, x equaling negative I. They are complex numbers, right? Okay. This theorem here is a complete factorization theorem, and all this says is kind of conjunction, I guess, to the last theorem, the fundamental algebra theorem. The polynomial will always be able to be factored down to a product of linear factors. Okay, we're going to continue to work with that stuff today, but using those two theorems to help us maybe work in a little bit of a reverse manner. Okay, this just talks about the zeros, and we've talked about this before. But if I had something like x, let's see here. You guys have something like x plus 3 to the fourth, x minus 1 squared. What's that polynomial going to be? What degree is it? A 6th degree polynomial. Okay. Everything is still maintained here in regards to the fact that we've got 6 linear factors. We just have 4 of them essentially that are not different, right? Okay. So our zeros don't have to be distinct. Our factors don't have to be distinct. To match up all the factors we talked about, the leading degree has to be equal to the number of factors we have and all that kind of stuff. We want to count our multiplicity in regards to our factors. So if I have a multiplicity of 4, I'm counting -3 as a 0 4 times. I'm counting +1 as a 0 2 times. So that's a total of 6 zeros. Even though they might not be distinct, I still consider them zeros. Does that make sense? Okay. So that's kind of a key thing to remember as we're doing these. I get people every once in a while say, well, I only got one factor here and one factor here because they're not different. Well, that's only going to be x squared. Well, if you multiply that out, you're going to actually get x to the 6. So that should then kind of confirm all of our other arguments. Yes? Yeah, so an even degree, so at -3 here, this thing is probably going to it'll come down here, and it'll be a little bit more flat and then bounce back up. If it's squared, it's more like parabolic there. But the higher the exponent gets in regards to even, the kind of the flatter or more kind of, I think it starts to look like a bowl shape or a cup at the bottom where it's really squared off. And that's because the values between 0 and 1, if we start raising to the 4th power, 6th power, 8th power, they get very, very small, very, very fast. So let's deal with some examples here. Okay, so this is what I'm talking about, kind of working our way backwards. This question is very, very, very similar to, if not the same, as what you saw in question 8 in the quiz. I don't give you a picture, but I give you all the information that you would have gained from the picture. Does that make sense? Now, on the quiz, they were. I didn't tell you if you had any like imaginary zeros or anything like that. But you have 2 zeros here that are complex or purely imaginary. They're all complex. When I say complex, guys, right now, I want you to understand that I'm probably meaning like a plus bi 4. Okay. So those zeros, I and negative I, those are purely imaginary zeros. You're not going to see on your graph their presence. Okay. Just like when I take a parabola and it doesn't cross the x-axis, right? We don't see the zeros because they're imaginary. We don't see their presence in the curve because the imaginary numbers are not part of the real number system. Okay. The real number system, the x and y plane, the coordinate plane, so the real plane is just your real numbers. Okay. We have an entirely separate plane called the complex plane that we'll get to at some point. Okay. When we get to the trig, we'll talk about that a little bit. But we can't graph I or any multiple of I or any sums and differences of I and any other real number like a plus bi or anything like that all in the xy plane. Okay. So you're not going to see these components in your graph, but they do end up being required. Okay. So it says I have a polynomial p of x, and we are going to have degree 4. Degree 4. So just kind of going off of what we've talked about so far, if I have degree 4, that degree is analogous to the number of factors that I'm going to have, right? So we can set that up right away. We should know now, degree 4, 4 factors. I should now be able to go through and say, well, all my factors, if I got zeros, all my factors are x minus those zeros, right? We can fill that in. We can go x minus whatever. And now I'm going to run through the sentence and say, okay, degree 4, zeros of I. Well, it's going to be x minus I, right? A zero of negative I. So x minus negative I. What's that turn into? Plus I. And then it's going to be a 0 of 2, so it's x minus 2. And x minus negative 2, so it's plus 2 again, right? Is that all right, everybody? Now, that is in kind of factor form. That's our polynomial, okay? Now, there's one kind of hiccup here that we haven't talked about, and it's this thing here, okay? Because if I were to graph this function, and let's see here, double check, x to the 4th minus 3x squared minus 4. For some, I got to mess around with why last class it wasn't letting me graph in the factored form for this polynomial. But if I take x to the 4th, that is minus 3x squared minus 4, that's not it. Did I? Idiot. There we go. You see how that has the zeros of negative 2 and 2, right? Okay. Now, you don't see any of the i's, plus or minus i's. The next thing says that this should be on my curve, okay? Now, what is that ordered pair? If I say p of 3 equals 25, what's the ordered pair that should actually be on my curve? 3 comma 25, right? So x of 3, y of 25. So I'm going to plot that. I'm going to see if that's on this curve. 3 comma 25. Zoom out. Is that point on my curve? No, it's not on the green curve, right? It's not there yet, okay? And how do I get that? It's because, how do I get it to be on the curve? It's because this here is just a general form. It is this idea here that there is some multiplier out here. We've been calling it A, that we can allow to be anything that I want to be. And essentially, it's just talking about the vertical stretch. Does that make sense? Okay. So what does that vertical stretch need to be so that my curve does go through A? 0.5. Okay. And my hopes are you see, guys, then that all our y values getting stretched as that A changes, but the negative 2, positive 2, and zeros are staying the same, right? So there's an infinite number of curves that go through those. We want the one that goes through those, that also goes through 3, comma 25. So how do I find that algebraically? Well, they're telling me right now we've got this expanded. Or sorry, not you could expand it if you want to. I'm not going to right now. So this tells me that when x is 3, y is 25, right? Or p of x is 25. So this thing here is 25 when my x values are 3. I'm going to go through here and I'll replace my x values with 3. And if it's just your choice, okay, I'm not saying that one way is better than the other, but you could have foiled that blue p of x out first and then went back and plug in x to be 0. It might be quicker, I don't know. But I've also, so I'm looking for, remember we got this A out here, I have it written in there, but we're looking for that A. So we got to have that as well. We got to have a variable in there to solve for. Now here's what's nice about this. What are those two things called in comparison to one another? They're conjugates. And the nice thing about conjugates, the reason we had conjugates in the definition for them is because we found out that when they're of that form, when they have the same terms, but one is plus and one is minus, and when I FOIL them, the O and I's become additive inverses, right? They drop out. They're opposites. Okay? So I don't need to FOIL this. I'm just going to go first comes first, which is 9, and then last times last, which gives me negative I squared. Anybody remember what I squared is equivalent to? Negative 1. So we got, let me rephrase it. We got 9 minus negative 1, right? 9 minus negative 1. What's that turn into? Okay. Now I got 3 minus 2, which is going to be 1, right? And 3 plus 2, which is 5. So what have I got on the right-hand side? 58. 45 on the left, right? That's all for A. 25 over 50. There's my 1/2 that we're looking for, right? So now I can come up to my P of X. And this is just you have to pay attention to how they ask you. Okay, if they're trying to target just your understanding of zeros and the factors that come from those, and this idea of finding the correct A, the correct scalar that's going to do the appropriate stretch, they might ask you just leave it that way. Okay, on a test, if I have 2 or 3 of these, I'm going to let you. Let's say I had 3 of these on a test or a quiz. I'm going to let you on 2 of them leave them like that. Okay. On 1 of them, I'm going to ask you to expand it because I want to see if you can do that. Okay. So let's go ahead and expand this. Meaning that it's got a FOIL, right? Well, if I'm going to FOIL this thing, it's all multiplication. So does it matter which terms I multiply together, first and second and third? Can I multiply x minus I times x minus 2? Yeah. Does that make sense? No. Why not? Yeah, because x plus I and x minus I are conjugates. X plus 2 and x minus 2 are conjugates. So we should probably multiply them in their groups of conjugates, right? Now, as you guys work through other examples and other problems, your conjugates might not line up right next to each other. But you can move them around if you need to. Okay? So I multiply these together, I get x squared. Okay? Now, O and I are going to disappear, so I don't need to worry about those. But now I have negative I times I. This means negative I squared, right? What was I squared? Negative 1. So I got minus negative 1, which turns into x squared plus 1, right? Okay? Now, this over here, x squared minus 4, right? I got my 1/2 out here. Now it's just another iteration of FOILing. X squared times x squared gives me x to the 4th. X squared times negative 4 is negative 4x squared. 1 times x squared. Then 1 times negative 4. And I still have my 1/2 out in front. I'm going to distribute that through. I get 1/2 x to the 4th. I'll combine these x squareds and multiply by 1/2 at the same time, so you get negative 3/2 x squared minus then 2. And that then is the correct expanded function that is going to have the zeros of 2, negative 2, and the zeros of I, negative I, and also pass through 3.5. So here's the idea, guys, is that we've been working so far on starting with what I've got in the box there, right, in that blue box again, and working to get I, negative I, 2, and negative 2. Now to say now we can do that, let's reverse the roles. Let's start with that information and see what the polynomial that we get from that information looks like. Okay? Again, it's just something you got to pay attention to in your homework, test quizzes. If they want you to expand, expand it. If they don't say, here's my thought. If they don't tell me on a test or quiz, I'm going to do the least right? Bare minimum, all right? Because if I don't tell you you have to expand it or that you leave it in factor form, the easiest thing to do is leave that factor form, right? Okay? And then you got the argument. Well, you didn't tell me, so I'm just going to leave it this way, and then I can't fight that argument. Let's do B here. So find a polynomial q of x of degree 4 with 0 is negative 2, 0, and negative 2 is a 0 and multiplicity of 3. So again, I'm going to write out, it's degree 4, so if I wanted to put, like I did in the last one, 4 sets of parentheses, I could do that. But it doesn't really make a whole lot of sense because one of those has a multiplicity of 3, right? So let's just do that way. Let's just structure it that way. So now I know at least the overall structure. I know that negative 2 has a 0 and multiplicity of 3. So what should go here? X plus 2. And now 0 is also a 0, right? So this means that it's going to pass through the origin, okay? So what's that going to look like? Just that, okay? You can write x minus 0, x plus 0 if you want to, but then that just simplifies that. If you want to put parentheses around it, put parentheses around it, you don't need to, though, okay? Now here's the thing. It said find a polynomial. It didn't say find the polynomial, okay? I said find a polynomial because how many polynomials have that criteria? Infinite, okay? Do they give me other information to take that number of infinites and dwindle it down to just one? No, okay? So if you left it as that, that's fine. If you say your a term is essentially a 1, then you have found a q of x that has the criteria provided. If you, for some reason, say your a term is 1/9, you're still right because you found a polynomial that has that criteria presented. Does that make sense, everybody? So your a could be anything, okay? So what happens a lot of times is that they'll write something like this. They'll write maybe like q of x is equal to a times x plus 2 cubed, and then we'll say, well, a is an element maybe of my real numbers, okay? And then that's going to suffice to show you all of them. All right? You don't need to do that. Now, if I did say find all the polynomials of degree 4 with 0 is a negative 2 and 0 where negative 2 is multiplied by 3, that's what you'd be looking for. But on a test or quiz, when it just says find a polynomial, that's usually what's going to happen. If they don't give me any other information to find a, I don't care what you choose to be a. All right? Let's talk about expanding that because it can be kind of tedious sometimes. Now, it's not. I don't know if there's going to be a benefit to what I show you here in a moment because it is x plus 2 to the third, and 3 is a relatively small exponent. But if I made that like 7 or 8, are you going to want to factor that thing out that many times? No. There's some shortcuts to that. Like if I have x plus 2 to the 8, well, that's x plus 2 squared 4 times, right? Okay, so I can maybe use some of that idea, that concept to help me out. Do you guys remember this thing last year? The 1 over here, the other side of that board. Have you guys ever seen something like that? That's Pascal's triangle. Good, okay? And what Pascal's triangle allows you to do is this binomial expansion. Okay, taking x plus 3 or x plus 2 cubed and expanding it. Okay, now here's the idea: is that this is the 0th exponent. This is the first exponent. This is squared. This is cubed. So we'd be looking at that line right there. Okay. Basically, what those numbers are telling me my exponent, or sorry, not telling my coefficient of my polynomial when I expand it. Okay, so I'm looking at trying to expand x plus 2 cubed. So my coefficients are going to be 1, 3, 3, and 1. Okay. Now, if you remember kind of the way that binomial expansion was kind of introduced to you, you always started with an a plus b, and a and b could be anything they wanted to. And let's say that I had it raised to the 3rd power. and it's going to look like this, okay? And then my objects are going to be, you know, I put A times B, A times B, A times B, A times B. You guys remember doing that? Okay. And then, okay, so now I got to remember what am I really doing? A plus B cubed means A plus B times A plus B times A plus B. If I were to FOIL all that out, just my first term, A times A times A, it'd be A cubed, right? It'd be, I didn't use any B's there, so it'd be B to the 0. So this would be cubed into the 0. Okay? So my first object is always raised to the third power, or my n power, and then this is to the 0. And now as I go through, what happens to, what's going to become the exponent here for this A? So it'll be 2, so they decrease. And what's going to be the exponent for B? 1. So this is going to become 1, and then 2, and then 0, and 3, right? If I'm doing x plus 2, what's A? X. What's B? 2. So I'm going to go 1, x cubed through the 0, plus 3, x squared through the first, plus 3, x to the first, 2 squared, plus 1, x to the 0, 2 cubed. Right? You can either write this, like, obviously I'm writing it down so you can see it, but maybe some of you would probably be doing some of this stuff in your head maybe. What's x cubed times 2 to the 0? X cubed. Okay? 3x squared times 2, 6x squared, right? Okay. 3 times 2 squared is 12x. And then x to 0 is 1 times 2 cubed is 8. So that expands x plus 2 cubed for us. Okay. Now, is that the only way? Absolutely not. You can take, if you wanted to, do it up here. You go x plus 2, x plus 2, x plus 2. Weird. If I FOIL those two, it gives me x squared plus 4x plus 4, then times x plus 2. And now I just got to distribute that as well. So x squared times x gives me x cubed. X squared times 2 gives me 2x squared. 4x times x gives me 4x squared. 4x times 2 gives me 8x. 4 times x gives me 4x. 4 times 2 gives me 8, right? If I start combining those, x cubed, 2x squared, 4x squared gives me my 6x squared. 8x plus 4x gives me 12x, and then plus my 8, right? So either way works. Either way is fine, okay? But do I want to do that top method if it's x to the 14th? No. I probably only want, to be honest with you, I probably don't want to draw a Pascal's triangle up to the 14th. To actually do the 15th power that I have to go, or 15th line. I wouldn't want to do that. But that binomial expansion is going to be a much quicker way of doing that than actually sitting down and doing the kind of the brute FOILing. Does that make sense? So those are options. And the reason I show that, are we going to use that a lot in this class? Probably not. I'm going to give you multiplicities that are relatively small, 3, 4, 5, that you could, if you need to, do the brute FOILing. But when you get to calculus, calculus is a new course. Calculus is no longer algebra. So the assumption is, once you got calculus, you have mastered, you have learned every single concept in algebra 1, 2, and 3 that are going to allow you to function inside calculus. So that might be something that you have to use when you get to a calculus question. Does that make sense? And that, I think, guys, that's the hard part of calculus, is understanding that when I'm working inside it, the assumption is I am a master at algebra, okay? Which for a lot of people is not the case. Okay, we can always get better. I apologize. So when we FOILed that out, I deleted it. Okay, when we FOILed that out, I had what was it? X cubed plus 6x squared plus 12x plus 8. That was only x plus 2 cubed, right? I still need to distribute that x through, so it just changes the exponents all by 1. And that would be my q of x. Okay? Hopefully you start to see, maybe while on a test or quiz, I'm not going to have you expand every one of them, right? It's a little bit time-consuming. If you can expand one of them, I'm confident enough that you can expand 2 of them, 3 of them, 4 of them, that kind of stuff. All right? All right, so that gets us to what we call the complex zeros conjugate theorem, okay, or conjugate zero theorem. Sometimes we call it complex conjugate theorem. This one called conjugate zeros theorem. But if you go back to all the examples that we've done so far that had like one had I and negative I as zeros, one we factored and got x plus I and x minus I as factors. X plus I, x minus I are conjugates, right? Okay. What this theorem is saying is that if a plus bi is a factor or a zero of my polynomial, then its conjugate is a zero as well. All right, so complex zeros come in pairs. When I say complex, I mean a plus bi. They come in pairs. Okay, they come in conjugate pairs. Now here's the thing. If we read this, it starts bringing in this new letter z and this notation z bar. But if we were to take a textbook and look through our textbook, it never, ever, ever tells you what z is. It never, ever tells you what z bar is. And that's the hard part about mathematics, is that it happens all the time. You start reading stuff and they introduce some weird variable that we've never seen, some weird syntax that we've never seen, and we have to do some research then. Okay. Basically, what happens in the complex plane, every number is of the form a plus bi, right? Where our analysis, our further algebra that we do with understanding the complex plane, all the things that it provides us, using a plus bi with multiplication and division and that kind of stuff, kind of a pain in the butt. So what we normally do is we redefine anything that is of a plus bi, we just call it z. And we start then doing the work with the z instead of a plus bi. Okay? If that's the case, then its conjugate, a minus bi, we write it as z bar. Okay, that's how we read that. Anything has a bar over top of it usually is referring to either the complement idea in set theory or notation, or here it's talking about the conjugate concept. Okay, that's all those things mean. Basically says if z, which is a plus bi, shows up as a zero, then z bar, which is a minus bi, shows up as a zero. Okay, so the conjugate always come in pairs. So how does that help us? Okay, and we'll start with this tomorrow, but I want you guys to see, because your homework assignment is open, and if you want to work on it, you can start on it. This says you have a polynomial of degree 3. Okay, so shouldn't I have 3 spots? All right, we have a 0 of 1/2, so this should be x minus a half, right? This says we have a 0 of 3 minus I. Now, it's a quantity, so I'm going to write it that way. X minus 3i. But now I've run out of ideas. I've run out of information that provides me. They've implied the other 0 here. What's the other 0? 3 plus I. They come as conjugates. Okay? So 99% of the time, guys, when they give you a p of x to find, they're only going to give you one of the a plus bi zeros, and then they'll force you to understand the conjugate theorem to come up with the second one. Does that make sense? Now tomorrow we'll come back, because that foiling there is not bad, but I want to show you and explain to you the steps, because it does kind of get a little bit messy. We'll pick up there tomorrow. Hopefully finish 3.5, maybe start 3.6 tomorrow. I think I got set off for Friday.